Hey everybody, Trey here. Welcome back to another video. Today our focus turns to Nebraska, which continued to shine in the tornado department this year after its incredible showing in 2024. We're going to break down one of the more unique events of the year, the cyclic supercells that produced multiple tornadoes in the Nebraska Sandhills on April 27, 2025. On a day in which convective development was quite conditional over a broad area, western Nebraska defied expectations and produced a localized outbreak of tornadoes, including the widest tornado ever surveyed in the NWS North Platte County warning area. In this video, we'll break down the meteorology behind this setup, including why storm initiation was favored in Nebraska, why the environment was able to produce strong tornadoes, and the radar evolution of these storms. So without further ado, let's go ahead and get started. To begin the day on April 27th, the Storm Prediction Center outlined an expansive level 2 out of 5 slight risk from Montana and the Dakotas all the way down into West Texas. This was coincident with a large 5% tornado risk contour encompassing much of western Nebraska, as well as western Kansas and the Texas and Oklahoma panhandles. Large to very large hail was also a concern across this corridor, as were damaging winds. In their discussion, the SPC noted that predictability was low within the slight risk area due to nebulous forcing for ascent and a reliance on dryline convergence as the main mechanism for storm initiation. In other words, the prospects for storm initiation were unclear, but any storms that could develop and mature would pose a risk for all severe hazards. They noted that western Nebraska and West Texas may feature slightly higher chances for storm initiation, although still somewhat low, given the proximity of a surface low and a slightly more intense dryline circulation, respectively. We'll describe all this in more detail in a bit. Isolated storms ended up initiating in far northeast Colorado, moving into western Nebraska during the late afternoon and evening. The storms evolved into a supercell cluster that produced 7 tornadoes in cyclic fashion, beginning with a slender, long-lasting rope just before 0Z or 6 p.m. Mountain Time, southwest of the town of Bingham, west of Hyannis. This was followed by the widest tornado ever surveyed in the NWS North Platte County warning area, a 1.25-mile wide EF2 that tracked between Bingham and Ashby over a 19-mile, hour and 14-minute path. The cluster continued to produce tornadoes as it moved into Cherry County, with 5 additional tornadoes that occurred both before and after dark. The final tornado was another EF2 that tracked over Merritt Reservoir southwest of Valentine. Thankfully, these tornadoes weren't able to hit much given the sparsely populated nature of the Nebraska Sandhills, and many were rated EF unknown. Later on in the video, we'll analyze radar data to estimate the actual intensity of some of these tornadoes. Farther south down the dry line, western Kansas remained completely devoid of storms, and while a few storms did briefly develop and intensify in West Texas, they collapsed fairly quickly. Before we move on, I wanted to remind you about my new site, stormchasercoaching.com. Here you can find the most in-depth educational content specifically tailored to help you improve your storm chasing skills, created by some of the best storm chasers and meteorologists in the world. If you're someone who wants to start your storm chasing journey safely and effectively, or you're a veteran chaser who wants to improve your game, Storm Chaser Coaching is for you. To help you get started, we're giving you our entire Storm Chasing 101 course for free. That's right, that's 2 hours of in-depth content taught by me that lays out all the basic foundations you need to chase safely and successfully, completely for free. Check out the link in the description box below to access our Storm Chasing 101 course. Also, join our free Discord community to connect with our coaches and other like-minded severe weather enthusiasts at the link in the description. For more information on what else we have to offer, visit stormchasercoaching.com. Now, back to the video. Alright, let's dive into the meteorology behind this setup. We'll start, as we always do, at 500 millibars at 12Z, 7 a.m. Central Daylight Time, on April 27th. Right away, your eye is probably drawn to this fairly highly amplified trough or closed low across the western U.S., the center of the closed contour there in central Nevada, with the axis stretching down through California into the Pacific. Somewhat of a positively tilted nature to this trough to start the day. Now, the problem is this is quite a ways farther to the west than what we'd like to see on the morning of a big plains severe weather event. Usually you'd like to see your trough a little bit closer to your area of interest so that it can eject into your area of interest at the peak of diurnal heating during the afternoon. That was certainly not the case with this trough, and as we go through the full loop here, you can see just how much the trough hangs back to the west during the event, it really never ejects into the plains during the afternoon or evening, leaving the plains in a bit of a void as far as large-scale synoptic forcing for ascent goes. The trough really doesn't start to fully eject into the plains until much later in the event, really by the following morning on April 28th. And you can really see how slowly this trough was moving by doing our Omega project analysis, in which we look at the translation speed of the 500 millibar jet max. If you're not familiar with the Omega project calculations, we take the midpoint of the jet maximum at 6Z the night before the event and compare it to the midpoint of the jet max at 0Z the evening of our event. So we're looking for how much the jet max has moved in that 18-hour period. Starting at 6Z the night before our event, looks like our jet max is going to be here, this little lobe of enhanced winds within the broad southwesterly flow rounding the base of the trough. Just eyeballing our midpoint at 6Z, it looks like it's somewhere there on the northern tip of the Baja California Peninsula. And then we fast forward to 0Z the evening of our event, and you can see visually that that jet max is not moving a whole lot. Our midpoint at 0Z is probably somewhere right in here in the middle of that 70-knot contour, and we don't even need to do the full calculations. You can see how little distance is between those 2 points, indicating a very, very slowly moving jet max. No doubt this is much, much lower than our 40-knot threshold for tornado outbreaks. Usually 500 millibar jets that translate at a speed of above 40 knots tend to favor more significant tornado outbreaks, and in this case, we are much below that threshold. We would need a much faster moving jet, given the starting position of the 500 millibar trough, to have given us more confidence in an overall more widespread event within the risk area on the evening of the 27th. So the bottom line is that synoptic scale forcing for ascent in this setup was very weak, given the fact that we were really not feeling the effects of the trough at all, and instead just kind of entrenched in this broad southwesterly flow ahead of the trough through the afternoon. That means we'd have to rely on, as the SPC noted in their morning outlook, surface features such as convergence along the dry line to allow storms to initiate. Now, speaking of this southwesterly flow, it was beginning to traverse the Rockies early on in the event and would continue to do so throughout the day. And as such, you'd expect to see surface cyclogenesis somewhere on the east side of the Rockies. Now, in our breakdown video on the March 14th, 2025 event, we talked about the math and physics behind the Lee cyclogenesis process, so check that out if you're interested in that. But the main thing here to note is that we had broad southwesterly flow traversing the Rockies over an extended period, and that typically induces surface cyclogenesis on the east side of the Rockies, somewhere in the eastern Colorado or eastern New Mexico vicinity. We'll talk about this more in just a bit. Up at 300 millibars, we see our trough across the western U.S., and we do see a little bit of defluence in the exit region of the trough. That's spreading apart of the wind vectors in the upper atmosphere that induces rising motion that we need to initiate storms in a given severe weather environment. Winds across the Intermountain West almost out of the due south, transitioning to more southwesterly flow across Colorado and New Mexico. And this defluence would start to overspread portions of the central high plains by the afternoon. As you can see at 21Z, 4 p.m. Central Daylight Time, we are starting to see a little bit of that defluence overspread the central high plains, including northeast Colorado and western Nebraska. Winds across Wyoming out of the south-southwest, transitioning to southwesterly over northwest Kansas, placing northeast Colorado and western Nebraska right in that area of defluence. And this may be one of the critical reasons that this area was actually able to initiate storms, unlike areas farther to the south. Despite the fact that synoptic scale forcing for ascent was weak across the entirety of the plains, we did perhaps have just a little bit of extra forcing here from this defluence aloft, and this rising motion may have allowed storms to initiate and persist across western Nebraska. You can see farther to the south, not much change in the wind direction at all, indicating a lack of defluence and very nebulous forcing for ascent on the synoptic scale from western Kansas southward. Down at 700 millibars, let's take a look for any short waves that may have impacted the central high plains during the day. And as we go into the afternoon, you'll see a little bit of a short wave develop from Colorado down into the Texas and Oklahoma panhandles. Here we are again at 21Z, 4 p.m. Central Daylight Time, and you'll notice this little bit of a kink in the height contours across this area. This was a little bit of a short wave that developed that was associated with a deepening low-level cyclone, which we'll talk about in just a bit. This was kind of the mid-level reflection of that. Short waves provide a little bit of extra forcing for ascent right out ahead of their axis, and by the afternoon, that would put northeast Colorado and western Nebraska in that favorable area for ascent. And that shortwave would start to move off to the northeast through the afternoon and evening. By 0Z, 7 p.m. Central Daylight Time, you see that little shortwave moving into western Nebraska and central Kansas, maintaining that subtle forcing for ascent out across the area where the storms were ongoing, allowing them to persist. Down here to the south, from western Kansas down into the Texas and Oklahoma panhandles, we were behind that shortwave now, which is a favored area for subsidence or sinking motion, which is not favorable for storm initiation and maintenance. All right, let's head down to the surface to see how things progressed throughout the day, because as we said, with the lack of synoptic scale forcing for ascent, we were going to have to rely on other things such as surface features to get the job done. Starting at 12Z, we really don't see any evidence of notable surface features yet. We don't really see any evidence of a surface low developing, don't really see any of that counterclockwise turning of the wind barbs in a given area that would indicate a surface low. And overall, this was not really a surface pattern that favored robust severe weather. Dew points just in the low to mid 50s farther north with mid to upper 50s farther south. These values are definitely on the lower side for significant severe weather events. Typically in late April, you'd want to see dew points in the 60s at least to get the job done. But as we said, with the southwesterly flow aloft traversing the Rockies, that was likely to induce surface cyclogenesis at some point in the eastern Colorado vicinity, which would allow the surface winds to strengthen out of the south or south-southeast, pulling moisture northward into our area of interest. And at the start of the day at 12Z, most of that moisture was confined to areas south of the Red River, mid to upper 60s dew points and even some 70s down here across much of Texas into far southern Oklahoma. So once surface cyclogenesis was underway, we'd see those winds strengthen, pump that moisture northward into the Texas and Oklahoma panhandles, western Kansas, and perhaps up into western Nebraska, which would aid in the severe weather threat. As we went through the morning into the early afternoon, we started to see signs of rapid surface cyclogenesis in northeast Colorado. Our surface winds had begun to show a little bit of cyclonic curvature across the region, and surface pressures had started to fall drastically. Just eyeballing it, it looks like our lowest pressure is here at Denver in northeast Colorado, sub 1,000 millibars there, so the center of our surface low at 18Z would go somewhere near that station. Our warm front was draped off to the east, then down to the south through western Kansas and northern Oklahoma. This was a bit of a weak warm front at this time, but we do see a bit of a temperature gradient, temperatures in the 70s and low 80s to the south and west of the boundary, 60s off to the east, with perhaps a little bit of a wind shift, more due southerly winds on the south side of the boundary, with slightly more backed flow on the east side. We also see quite a bit of cloud cover on the cool side of the boundary. Notice how the central circle of each station is filled in across a widespread area on the cool side of the boundary, with much more open circles here on the warm side, indicating a fairly cloud-free environment on the warm side and a much more overcast environment on the cool side. So our warm front was a little bit difficult to place at this time, but if I had to eyeball it, it would be somewhere in there. Now, as the surface low began to take shape, our surface winds began to intensify, allowing a dry line to tighten across the high plains. At 18Z, it looked to be somewhere in here, with dew points in the teens, 20s, and 30s on the west side of the boundary, with dew points in the 50s and 60s on the east side. As we had expected, the richer Gulf moisture that was located down in Oklahoma and Texas to start the day had begun to creep northward, with upper 60s to low 70s dew points up to the Kansas-Oklahoma border, and low 60s dew points all the way up into southwest Nebraska. The surface low continued to deepen through the afternoon. By 21Z, 4 p.m. Central Daylight Time, a surface low center was evident near Denver once again, where pressures were lowest, but this was a broad surface low. I won't do a full surface analysis here, but this was a very expansive surface low with likely multiple surface low centers within the broader cyclone. This included potentially one up near the Nebraska-Wyoming border. The warm front continued to stretch down to the southeast through western Nebraska and much of Kansas, while the dry line continued to tighten and shift off to the east just a little bit, now extending from the northern surface low center through western Nebraska down through the Kansas-Colorado border region into the Oklahoma and Texas panhandles. Robust moisture continued to stream off to the north, with 60s evident all the way into western Kansas and southwest Nebraska. Although surface convergence was fairly weak along the dryline boundary, we don't see a very strong wind shift on either side of the boundary, maybe just a subtle shift from south-southwesterly to more due southerly. This did not bode particularly well for convective initiation in Kansas, where synoptic scale forcing was quite weak. However, up in western Nebraska, surface convergence was quite a bit stronger given the proximity of the northern surface low center, the intersection point between the warm front and dry line, and the dry line bulge that was evident. Notice how the dry line kind of bulges outward across western Nebraska and northeast Colorado. Dry line bulges are often a favored area for storm initiation because surface convergence is often strongest at the apex of the bulge. This was likely another critical factor that allowed for storm initiation in northeast Colorado. Both synoptic scale forcing for ascent and surface convergence were strongest in this area, lending much higher confidence in storm initiation compared to areas farther south. Interestingly, down in West Texas, we did see a little bit better convergence along the dry line with southwesterly winds on the west side of the boundary, with much more backed or southeasterly flow on the east side. And lo and behold, this was a favored area for storm initiation, despite the weak synoptic scale forcing for ascent. By evening, the surface low had consolidated and moved into western Nebraska. The warm front was still draped down to the southeast, and the dry line to the south. The supercells were occurring along or just to the north side of the warm front, allowing them to tap into a little bit more backed low-level flow, and temperatures just north of the warm front were not prohibitively cool for surface-based convection. Still, you might take a look at this surface map and say that upper 50s to low 60s dew points are really marginal for significant severe weather, including tornadic supercells. And usually you'd be right. If this was central Kansas or central Oklahoma, we'd probably be dealing with more of a damaging wind and large hail threat rather than a tornado risk. The kicker here is terrain. Western Nebraska has quite a bit higher terrain than areas elsewhere. Air at higher elevations doesn't hold as much moisture by nature, so a dew point of, say, 60 in western Nebraska is like a 70-degree dew point at somewhere like Oklahoma City. We talk about this a lot in tornado cases in eastern Colorado or eastern Wyoming, but I don't think people realize how similar western Nebraska is to these areas. When you have those southeasterly surface winds, you have that nice upslope flow up that higher terrain, and the terrain influences can create areas of enhanced vorticity or low-level shear that can induce tornadogenesis in supercells despite somewhat weak low-level shear in the ambient environment. Combine that with a lesser amount of moisture that's necessary for tornadic supercells, and you get a lot of these kind of sneaky events in western Nebraska that sometimes are hard to forecast ahead of time, but can provide some pretty spectacular results. Dryline convergence remained fairly minimal in western Kansas by early evening, which was a likely factor in the blue sky bust there. But down in West Texas, particularly near the Lubbock area, that dryline convergence persisted from the afternoon, again aiding in storm initiation down there. At 850 millibars, a modest low-level jet was in place to start the day across much of the plains, particularly across the central plains. 30 to 35 knots of flow was common from Kansas up into South Dakota. And as you might expect with a deepening low-level cyclone, the low-level jet was able to remain in place and even strengthen a little bit throughout the day. By the afternoon, 30 to 35, even 40 knots of flow were common across the plains. And by 0Z, we saw a broad swath of about 30 to 40 knots of flow from southwest Nebraska all the way down into West Texas. So clearly across this corridor, low-level shear was going to be quite strong, and we had a fairly volatile atmosphere for severe weather. We just needed storms to fire, and that mostly did not end up happening. Up in western Nebraska, we only saw about 20 to 25 knots of flow at 850 millibars, indicative of a somewhat weaker low-level jet. This is fairly common for these high plains setups, and as we talked about earlier, the terrain influence and some of that more backed surface flow was able to overcome the lack of a stronger low-level jet and aid in tornadic supercell production. The low-level jet continued to increase after dark to over 50 knots across a broad swath of the plains, including western Nebraska. Alright, let's take a look at some observed soundings from across the region to see how our environment progressed throughout the day. We'll take a look at a series of observed soundings from North Platte, Nebraska, Dodge City, Kansas, and Amarillo, Texas. Let's start off with North Platte, Nebraska, which of course is closest to our tornadic supercells. Now, unfortunately, NWS North Platte did not release a 0Z evening sounding, but we do have a morning sounding from 12Z and a special 20Z sounding, so we can at least see how the environment progressed from the morning into the afternoon. 20Z, of course, is right before storm initiation. Moving on to 20Z, 3 p.m. Central Time, and we're starting to see a bit more of a traditional severe weather sounding. The warm, unstable air mass had started to make its way up into the North Platte area by this time, 65 over 60 now at the surface with a well-defined moist layer, extending up to about 800 millibars or so, beneath a fairly stout capping inversion that remained at the base of the elevated mixed layer. Now you'll notice from 12Z to 20Z, we hadn't really seen a reduction of that cap like we would see with a strongly forced event. That cap had stayed pretty stout through the morning and afternoon, and that was due to the very weak synoptic scale forcing for ascent. Now, in higher terrain areas, this doesn't matter as much. The terrain can help force air parcels through that capping inversion to sustain convection, but by this time, the defluence aloft and the shortwave trough were starting to move into the region, which likely helped erode this cap a little bit more quickly. Plus, we had continued moistening and warming at the surface, which would also help to decrease the impacts of that capping inversion. So all in all, with all of those factors combined, the cap likely was neutralized in this area, and strong surface convergence near the dryline bulge and surface low, and the higher terrain likely helped focus convective initiation in this area. But all in all, a fairly loaded gun type sounding with decent instability aloft, 1300 joules per kilogram mixed layer CAPE, which is somewhat low for significant severe weather events, but certainly more than adequate for severe weather, especially in these higher terrain areas. And our kinematics remained fairly impressive, especially in the low levels. Nicely clockwise curved photographs there. We had maintained that low-level jet throughout the day, about 30 knots or so at 850 millibars, leading to just under 300 meters squared per second squared storm relative helicity. Now, deep layer wind shear was starting to increase. Photographs were lengthening a little bit. Effective bulk shear up to almost 30 knots, still on the margins for supercell activity, but those winds aloft were increasing from what we saw in the morning hours. Very weak winds aloft at 12Z, 15 to 30 knots between about 500 and 300 millibars, and those were increasing with time, now up to about 25 to 40 or 50 knots in that layer. So deep layer winds were increasing as the southwesterly flow ahead of the trough was impinging upon the region, leading to an environment that was adequately destabilized and adequately sheared for organized convection, including supercells. Moving on to Dodge City, Kansas, and at 12Z, a pretty similar look to that of the North Platte morning sounding. Fairly cool, moist low levels with a saturated air mass up to about 750 millibars or so, so pretty deep moisture. This was situated beneath a little bit of an elevated mixed layer with a capping inversion at the base of said EML. Once again, low-level kinematics were fairly impressive with that strong low-level jet in place, large looping photographs, but once again, somewhat weaker deep layer shear, sub 30 knots at Dodge City, Kansas as well, so we would also need that stronger flow aloft to start impinging upon the region to provide an environment favorable for supercells. But again, the question was, how would this cap erode through the day given the very weak forcing for ascent? Here we are at 20Z, and the moist layer had remained fairly deep, up to about 800 millibars or so, but that cap had remained pretty stout, pretty well-defined warm nose there at the top of the moist layer. And as we talked about, the surface convergence along the dry line was a little bit weaker here than it was, say, for example, in Texas, where those winds were coming together nicely along the dry line. In Kansas, that was not so much the case, even though the moisture gradient was quite tight. So here, because we were relying on the dry line convergence to get the job done, in the absence of large-scale forcing for ascent, this mid-afternoon sounding was a little bit concerning, given that we really didn't have a well-defined mechanism to erode this cap fully. And for storm chasers, that was a little bit of a shame because this environment certainly would favor tornadic supercells, including significant tornadic supercells should a storm fire. Ample instability, 2,000 joules per kilogram mixed layer CAPE, with large looping photographs. You see that deep layer shear increased to over 40 knots as the southwest flow overspread the region, with nice curvature in the low levels of the photograph, over 200 meters squared per second squared effective storm relative helicity. Now at Dodge City, we do have a 0Z evening sounding launch. So let's see how that cap did from mid-afternoon to early evening. And you see that we weren't really able to fully erode this cap. We still had a bit of a warm nose atop the moist layer at 0Z. And again, because dryline convergence remained fairly weak and synoptic scale forcing for ascent was weak, this cap was a little bit problematic. When you have a strongly convergent dryline or any other strong boundary or other mechanism like terrain or something to force air parcels upward through that remnant warm nose, this is really not a problem. But storms trying to go up in this environment were struggling because of this remnant warm nose, and any towers that tried to go up along the dry line just couldn't get the job done. We did have quite a bit of drier air aloft as well, so as those updrafts were struggling with the capping inversion, they were also ingesting a lot of that dry air, which allowed them to kind of pinch off and dissipate. But you can see, had a storm fired, we would have had a chance for all severe hazards, including tornadic supercells, with moderate to strong instability, 2200 joules per kilogram mixed layer CAPE, adequate deep layer shear of about 40 knots, and nice looping low-level hodographs with ample streamwise vorticity. That storm relative wind vector in the low levels very much parallel to the horizontal vorticity vector, which is perpendicular and to the left of the hodograph, really through the lowest kilometer of the atmosphere. But this environment did go to waste here, and it remained a blue sky bust. Down at Amarillo, Texas, things looked pretty much the same to start the day, with a moist layer beneath a pretty stout capping inversion. But watch what happens to the capping inversion through the day. Here we are at 21Z, and we really don't see any additional evidence of a cap in place. So capping was a little bit weaker farther south. We were more fully destabilized, and the overall instability was stronger down here as well. 3,300 joules per kilogram mixed layer CAPE. Pretty fat CAPE profile as well. 74 over 65 at the surface, so surface moisture was a little bit higher than areas farther north as well, coupled with a favorable profile for organized convection, including supercells, with a lengthy hodograph, over 50 knots of effective bulk shear, and a curved low-level hodograph. This persisted into the early evening. Here's the 0Z sounding, still very strong instability, 3,600 joules per kilogram mixed layer CAPE, and a hodograph favorable for supercells with all hazards. So the lack of capping this far south was a reason why storms were able to at least initiate down here as well. Also, the fact that we may have had a slightly stronger dryline circulation. Temperatures to the west of the dryline were a little bit warmer than they were farther to the north, with some stations reaching the low to mid 90s in eastern and southeast New Mexico, compared to upper 70s to 80s across eastern Colorado. Hotter temperatures on the west side of the dryline often mean a deeper dryline circulation, which can make it easier for storms to develop as well. But temperatures were quite warm east of the dryline as well, with somewhat more limited moisture, especially where they developed southwest of Lubbock. 88 over 55 at that station there, just south-southwest of the Lubbock area. So very high temperature dew point spreads led to more outflow dominant storms, and with a lack of synoptic scale forcing for ascent, they weren't really able to sustain themselves after they gusted out. The first signs of convective initiation occurred just before 21Z, or 3 p.m. Mountain Time, 4 p.m. Central, in extreme northeast Colorado and western Nebraska. The expanding cumulus field with time indicates synoptic scale forcing for ascent was starting to overspread the region. Eventually, one of these updrafts became robust as it moved north-northeast into the Nebraska Panhandle, eventually becoming our initial tornado producer. As we dig into the radar data for this case, you'll see how important storm mergers were in both intensification and tornadogenesis. Here is our main storm that went up just north of the Colorado-Nebraska border. As we go forward in time, you'll see that it kind of struggles for a little bit, but we have a couple of new updrafts that develop just on its southern flank. And as it continues to move north, these updrafts kind of merge with the initial storm, and then they become one more intense storm. So it's likely that the merger of those updrafts allowed for intensification into a dominant supercell. When you have updrafts kind of clustering together and merging like that, that can help overcome any deficiencies in the environment, such as remnant capping, strong wind shear, dry air. In most cases, it's very difficult for a single updraft to survive, but when they cluster together and start merging with one another, that can help overcome the deficiencies in the environment to allow for a better chance of storm intensification. As we continue on, you'll see a new updraft develops just south of the ongoing dominant supercell. This is going to become critical in the lead up to tornadogenesis. Over the next several minutes, the updraft starts to grow in size, and actually the dominant supercell begins to split into two separate supercells. Notice how we have two distinct cores, indicative of two separate updrafts, and that the storm has split. At this point, the rightmost supercell becomes dominant. The updrafts to the south continue to move to the north toward the now dominant supercell. And then about 15 to 20 minutes before tornadogenesis occurs, we start to see these updrafts intensify in the inflow region of the dominant supercell. Over the next few minutes, they then merge with the dominant supercell, and you can almost see the immediate impacts. Once the merger occurs, a well-defined hook echo becomes apparent. In reflectivity, velocities start to increase. We see rotation start to ramp up. And at this point, tornadogenesis is underway now that we have a single, more intense supercell. And the first of the 7 tornadoes began at about 6:38 p.m. according to damage surveys. So it's pretty clear that mergers played a critical role in tornadogenesis in this case. The initial tornado would continue for several minutes before a new tornado began just before 7 p.m. west of Hyannis near the town of Bingham. This tornado would quickly become large and intense. Note the very intense velocity couplet, and at times this tornado would measure 1.25 miles wide. Also, notice the updraft that had developed east of the ongoing Bingham supercell. This updraft clearly had supercell characteristics as denoted by the bean shape on radar and the attendant hook echo that was developing, and visually as we see from this view about 15 miles east of Hyannis around this time. Note the tilt and rotation in the updraft. The new supercell continues to intensify while the Bingham tornado continues off to the west. Eventually, the two storms configure themselves into a supercell pair. As we've discussed before here on the channel, recent research from Nixon et al. 2024 suggests that the lead supercell in a supercell pair is most favored to produce tornadoes, while the trailing supercell tends to get undercut by the lead supercell's outflow. Also, note the new updrafts that had developed in proximity to the eastern supercell, and the fact that we now had a third supercell to the south of the supercell pair. All of these are going to be critical in the evolution from this point. The new updrafts now merge with the easternmost supercell, allowing it to intensify. The core beefs up, rotation starts to increase. By this time, the southernmost supercell had inched closer to the supercell pair, now impeding the inflow to the westernmost supercell, which was dominant. In other words, the inflow that the westernmost supercell was ingesting was now cool and stable. As a result, the Bingham tornado begins to weaken. Subsequently, a brief new tornado occurs just east of the dissipating Bingham tornado. This appears to have been a slender rope that lasted for 6 minutes. But then the easternmost supercell becomes dominant, leading to new tornadogenesis at 8:12 p.m. This tornado would last for about 15 minutes over open land northeast of Hyannis. The southern supercell then merges with the ongoing former Bingham supercell, while another new supercell develops on its southern flank, quickly becoming intense, complete with a hook echo. The original tornado northeast of Hyannis dissipates while rotation increases on the new southern supercell. According to damage surveys, there was a lull in tornado production from the dissipation of the tornado northeast of Hyannis until just before 10 p.m., despite the supercell exhibiting strong low-level rotation. During this time, new updrafts developed on the western flank of the supercell and morphed into a new supercell. I'd be surprised if the main eastern supercell was not tornadic at this point, given the tightly wound hook echo and intense low-level rotation, perhaps aided by a nudge from the western supercell, as described in work by Cameron Nixon. Supercells need a perfect balance of inflow and outflow to become tornadic. To balance out the inflow going into a supercell, you need a source of outflow. Where does this outflow come from? Auxiliary cells in proximity to the main supercell. Subsequently, the new western supercell takes over and becomes dominant, while the former eastern supercell dissipates. Low-level rotation then begins to increase with the new dominant supercell. We don't really see any nudgers here, but that doesn't always matter. The environment can do the work in some cases. We'll look at some proximity soundings here in just a bit. Then something interesting happens. The mesocyclone almost appears to split into two different mesocyclones. Let's take a closer look at this. We start off with a single large mesocyclone with an attendant hook echo. Then, over the next few scans, we see the development of a new mesocyclone. The original one continues to move off to the east, while a new one develops just to its west. You can also see two separate hook echoes here. Here is our original hook echo with our original mesocyclone, and this new hook echo that develops to its west associated with the new mesocyclone. These dual mesocyclones would persist for quite a while, and tornadogenesis occurs with the new western mesocyclone at 9:53 p.m. Again, note that we have two distinct velocity couplets and two distinct hook echoes. The tornado-producing mesocyclone acts like it's occluding with a due north motion pretty much from the get-go. This yields a complex evolution leading up to the final few tornadoes of the event. Now, just to set the stage once again, we have our easternmost mesocyclone, which was the original mesocyclone with this supercell. We have our tornado-producing occluding mesocyclone to the west, and we have an auxiliary storm on the western flank of the occluding mesocyclone. The occluding mesocyclone to the west merges with the storm on its western flank, and then the other original mesocyclone appears to occlude itself, shooting northwest and merging with the western mesocyclone. This leads to tornadogenesis southwest of Valentine. The new conglomerate mesocyclone first spawns an EF1 while the mesocyclone merger was still ongoing. Then once the merger was complete, it spawns an EF2 near Merritt Reservoir. This tornado became very large, up to a half-mile wide at times, and quite intense. A satellite tornado develops around 10:41 p.m. just south of the main tornado. This was suggested by radar and visually, as seen in this video from around 10:44 p.m. southwest of Valentine. Now, as we know, the Nebraska Sandhills are extremely sparsely populated with very little for these tornadoes to hit. Still, the Bingham and Merritt Reservoir tornadoes were rated EF2, but let's estimate the intensity of these tornadoes from radar data to see how accurate these ratings are. We can estimate a tornado's intensity using radar velocity data, starting by calculating a variable called delta V, which is essentially the total wind shear across the TVS. In mathematical terms, it's the difference between the maximum outbound and maximum inbound velocity within the vortex signature. However, the relationship between delta V and tornado intensity is an outdated concept, and recent peer-reviewed research suggests that rotational velocity, or VROT, is a much better proxy for tornado intensity from radar data. VROT is simply half of delta V, and when combined with an estimate of tornado potential in a given environment, specifically significant tornado parameter, or STP, it can give us an estimate of tornado intensity in real time, as illustrated in Smith et al. 2020. I went through and manually calculated VROT for a few different scans during the Bingham tornado's life cycle, particularly those that showed the strongest velocity couplets on radar. During the early portion of its life cycle, VROT values approached 90 miles per hour, and in one scan in the latter half of its life cycle, VROT exceeded 100 miles per hour. The Bingham tornado was occurring near an STP bullseye of 6, although it was slightly removed from the STP maximum. So conservatively, we'll say significant tornado parameter was about 4 to 5 in this case. Using figure 9 from Smith et al. 2020, which shows box and whisker plots for certain combinations of STP and VROT, compared to peak wind speed via damage indicators for tornadoes satisfying each STP-VROT combo, the Bingham tornado falls into this box and whisker plot here, which denotes STP between 1 and 5.9 and VROT greater than or equal to 70 knots or 80 miles per hour. Tornadoes satisfying this STP-VROT combo tend to have damage-indicated wind speeds between about 110 and 140 miles per hour, with lower and upper bounds of 100 and 170 miles per hour respectively. This means that most tornadoes satisfying this STP-VROT combo tend to be rated in the EF2 to low-end EF3 range, with ratings as high as low-end EF4. So it appears the Bingham EF2 was fairly well rated, but possibly may have been more intense than the rating suggests. The Merritt Reservoir EF2 southwest of Valentine had VROT values over 100 miles per hour and slightly greater STP at 6 to 7. That places it in this box and whisker plot here, which has a third modulating factor of population density of less than 20 people per square kilometer, which of course is the case in the Nebraska Sandhills. Tornadoes that satisfy this STP-VROT combo tend to have damage-indicated wind speeds between about 120 and 155 miles per hour, with lower and upper bounds of 110 to 180 miles per hour respectively. So it's likely that the Merritt Reservoir tornado was actually a bit stronger than the EF2 rating suggests, perhaps as high as a low to mid-range EF4. Of course, this is all conjecture because of the lack of damage indicators in the Nebraska Sandhills, but it's interesting to see how these tornadoes might have been rated had more notable damage occurred. Finally, let's take a look at some RAP model soundings in proximity to the supercells in western Nebraska to see how the near-storm environment progressed throughout the day. These were pulled from a location just southwest of Bingham, and shout out to the Chase Archive for providing these soundings. Starting off at 13Z, which is 7 a.m. Mountain Time, 8 a.m. Central Time, and we see a very similar look to what we saw with the observed sounding from the morning at North Platte. A very stout capping inversion at the base of the elevated mix layer. Again, we were still well north of the best air mass at this time, 53 over 52 at the surface. So we had a long way to go to destabilize at this point. Still some leftover low-level jet at this time, a little bit of curvature in the hodograph, but deep layer shear was on the weaker end, as we mentioned earlier, below 30 knots, which is only on the margins for supercells. Going through the morning into the afternoon, we saw slow destabilization as temperatures warmed and dew points moistened just a little bit at the surface, but with the lack of forcing, that cap remained pretty stout until initiation time. This is at 21Z, so right about initiation time. And notice now the RAP suggests we were fully destabilized with really no more remnant cap. This does make sense because, of course, storms were able to initiate and become mature at this time. And as the subtle forcing aloft started to overspread the region, that likely helped the cap erode a little bit more quickly. This is certainly a much different look than what we saw with our 20Z observed sounding at North Platte, which still had a very stout capping inversion in place. Instability overall was rapidly increasing up to about 2,300 joules per kilogram as progged by the RAP at this time. And deep layer shear was increasing as well. Hodographs had lengthened, and 0 to 6 kilometer shear was up to almost 40 knots at this point as those winds aloft began to strengthen with the approach of the incoming shortwave. So all in all, this is certainly an environment that would favor supercells with moderate to strong instability and strong deep layer shear. Low-level shear at this time left a little bit to be desired, but again, sometimes it just doesn't matter in a higher terrain region like western Nebraska. But with the continued deepening of the surface low, these hodographs wouldn't remain stick straight for much longer. Moving forward to tornado time, and by then, soundings were pretty impressive. Here we are at 0Z as the Bingham tornado was ongoing, and we'd seen a few things happen. Now 67 over 61 at the surface, dew points had moistened. The dew point was now in the low 60s, so we'd seen moistening as the warm sector had advected northward through the day. And again, this is pretty rich surface moisture for such a higher terrain region like western Nebraska. It'd be very similar to, say, a 70 dew point at Oklahoma City. And the surface winds had backed quite a bit. Earlier we were dealing with much more southerly flow. Now those winds had turned to a more southeasterly direction, and they'd strengthened, leading to much more large looping hodographs in the low levels amid strong deep layer shear. 0 to 1 kilometer storm relative felicity at this time was just over 200 meters squared per second squared. And you couple that with this kind of an instability profile, over 3,000 joules per kilogram as progged by the RAP. This might be a little bit overdone. The RAP tends to be a little overzealous with the instability. But still, if you take a few hundred joules per kilogram off of that, we're still in the moderate to strong instability range with fairly thick instability all the way up through the profile. 0 to 3 kilometer cape was impressive as well. Here's your 3 kilometer level. Notice how much instability is packed in those lowest 3 kilometers. We can see this in the progression of the 3 cape and surface vorticity product in the SBC Mesoanalysis archive. The blue outlines here are surface vorticity or spin, and the red outlines are 3 cape. Starting in the morning and going through the day, you can see a rapid increase in 0 to 3 kilometer cape through the afternoon and early evening, up to about 125 joules per kilogram, right in a bullseye there in western Nebraska where the supercells were moving into by early evening. So the low-level environment was quite unstable. We've talked about the importance of this many times before on the channel. When you have strong low-level spin, strong low-level instability can really aid in tilting and stretching that spin into the vertical to aid in tornadogenesis in supercells. But all in all, you take a look at this profile, and this is a classic tornadic supercell profile, especially for a higher terrain area like Nebraska. Not too concerned with the low surface temperatures there. We were fully destabilized with moderate to strong instability, strong low-level and deep layer shear. In hindsight, this is a pretty classic look for significant tornadic supercells. Continuing into the evening, we see those hodographs continue to enlarge pretty drastically. By 2Z, those hodographs were jaw-dropping, to say the least. Over 400 meters squared per second squared of 0 to 1 kilometer storm relative felicity. Large looping hodographs as the low-level jet ramped up. 1 kilometer winds well over 40 knots, which maintained a very favorable environment for significant tornadic activity, especially with this kind of an instability profile. Minimal convective inhibition or capping building back in, but when you have high terrain and strong low-level shear to compensate for that, it doesn't really matter all that much. Really, this is pretty negligible. So we were able to maintain strong instability and strong low-level shear through the evening to allow for the supercells to persist and continue to produce tornadoes even after dark. So that's going to wrap things up for this video. Hopefully this gave you some insight into how Nebraska was able to go off like it did on April 27th. A combination of slightly stronger large-scale support from the approaching shortwave, defluence aloft, and favorable surface pattern, as well as a complex series of storm interactions and mergers, led to one of the more impressive tornado events of the year, at least from a chasing perspective. It goes to show how important careful analysis is throughout the day of a severe weather event, as the subtle clues that suggested Nebraska as the main target were easy to miss. Thanks for watching, and we'll see you in the next video.